what I'm going to do to start this talk is show you some dangerous code. And when I say dangerous, then what I mean is that this code is something I look at and say, well, sometimes we've seen this kind of code being exploited, but sometimes it's not exploitable. It depends on the context. It's something where you have to look at how the code is used, not just the code snippet, which is doing something dangerous, but the surrounding context. That's what shows you, is the code actually exploitable or not. It takes just a moment to look at it and say this is doing something dangerous. It takes much more work to try developing a timing attack. That's what the danger is an attacker is going to see your secret data from this code using timings of the code. Now, maybe when you try developing a timing attack, then you see, oh, no, it's safe, actually, as used in context. So what do you do in this situation when you see some code which is dangerous, but, well, maybe not exploitable? What I recommend is saying, replace the code. The code is doing something which is scary and sometimes breakable, so replace it with better code. But a lot of times what people do instead is something more reactive, where they say, if somebody demonstrates an exploit, then you fix the code. Otherwise, don't worry about it. Now, let me be clear about the trade-offs here. Maybe the code is not exploitable. Sometimes code like this is not exploitable. And then the reactive approach is saving time, because it's not doing any work until an exploit is demonstrated. And if the code is not exploitable, then why do the work? On the other hand, if the code is exploitable, then, well, the reactive approach is leaving users vulnerable. So the proactive approach is more work, but the reactive approach produces more security holes, which is kind of scary. So that's why I recommend the proactive approach. It's possible, these are just 2 points on a spectrum. It's possible to be less reactive. For example, if you demonstrate a timing attack, the way it works when people develop these timing attacks, what you end up seeing online is like, here's a timing attack demo that takes 10 minutes to run. But actually developing that is a long process. You might start with, you do an experiment that takes a day and it doesn't work. And then eventually, after 50 experiments, you have something, aha, I can retrieve the secret key in a day. But then that's not fun for people to reproduce. So you try to make it faster and faster. And after a lot more work, you have something which takes only 10 minutes. And then because you want to get rid of noise in timings when you're developing these timing attacks, you only carry out the attacks locally. Like you want to reduce noise and just have an easy, pure timing attack. If you carry out a timing attack remotely, there's more noise and you have to do more work to develop that attack. So many times people will demonstrate local timing attacks on the same system. And OpenSSL security policy says if you have an attack on the same system, that's not good enough for a CVE. You have to demonstrate a remote exploit in order to have an OpenSSL CVE for a timing attack. So that means that there's work being done only in the cases where somebody demonstrates a remote exploit and not in the cases where somebody demonstrates a local exploit. And okay, less work, but of course it's often leaving people even more vulnerable. Let me show you the code that I'm talking about. This is from OpenSSH with a file called libcrux mlchem768 SHA-3. You know what MLChem and OpenSSH and SHA-3 are. Libcrux is a cryptographic library, which is the source of this code. And I'm not going to go through all the code. I just want to focus on the last 2 computations. There's a shift right by 8, and then there's an and 1. Well, I say then because I remember the C precedence rules. I would put more parentheses into this to make it clear that it's shifting right by 8 and then doing and 1. Now, those last 2 operations, they're extracting a bit from whatever was computed before. And those operations, well, a compiler will sometimes look at this and say, I know a better way to do that. I know a single CPU instruction which will take those 2 operations and in a single instruction extract a bit and conveniently put it into a CPU flag, which you can then use for a branch. Depending on how the result is used, maybe you can save instructions by using a branch instead of doing some arithmetic. And the compiler will try to figure that out. And well, to see whether the compiler produces a branch, you have to look at how the result is used, which compiler are you using, which compiler optimizations are there, which optimization options you're using, what platform you're compiling for, and maybe things are okay in whichever application, but maybe they're not. We have lots of examples where things are not okay. So timecop is integrated into the supercop test framework for lots of cryptographic code, doing unified testing of cryptographic code. And well, timecop was producing some alerts in 2024, which I was tracking down to. There's a GCC patch, which starting in 2021 was converting, if you do have a 32-bit variable x, you negate it, shift it right by 31 bits, that produces a single bit output, just like doing AND1. And sometimes the compiler would say, oh yeah, that's something I should convert into a branch, which was taking various cryptographic software and converting it into variable time software, where otherwise the software was just fine. Another example from Anton Pernal in June last year was extracting secret keys from the reference Kyber software, which was using AND1 in the same way as the AND1 that you saw on the previous slide. Now, again, I'm not saying that the previous slide is exploitable. I haven't done the work to figure that out. All I see is there's AND1. That's scary. I have a link here to lots more examples, a survey of lots of examples of the compiler saying, aha, here's a single bit result, which I can convert into a branch, and sometimes does. So that's worrisome. The reason that I've taken the example from the previous slide, which is not an example where we know it's exploitable, but an example from libcrux, is that the advertising for libcrux says, libcrux, this library, gives you the highest level of assurance that it's safe to use and free of bugs. And nevertheless, we see in this code this AND1 being deployed in OpenSSH. So this is kind of scary. Thomas Pournat had a paper earlier this year called Constant Time Code, the Pessimist Case. It's great fun to read. I recommend it very much, which is going through some of these failures and saying why he expects the failures to become more common, making constant time coding infeasible in all generality. I also noticed in the schedule for this conference, there's a talk coming up, Constant Time Big Num is Bollocks, by Billy Bob Brumley. And I assume that'll tell us more of how hard it is to get constant time code actually working. Now, the situation is actually worse than this. If you look at these C compilers, they're not just producing timing variations in our cryptographic software. They're also just producing outright bugs in all sorts of software. And this is not a surprise because C compilers, GCC and Clang, these are these huge projects, tons of commits to these projects. And if you look through the commits, then, well, okay, sometimes there's like commits which are changing things about languages that you're not using, but a lot of times the commits are about optimizations. GCC and Clang, they're trying to make your code run faster. Well, not your code necessarily, but somebody's code run faster. And so they add some optimization, and then they add some tests for it, and then they realize the tests are not working correctly, so they fix the tests, and then they realize the optimizations are not working correctly, so they fix the optimizations. And this just keeps going and going and going because that's a huge part of what GCC and Clang are doing is trying to make your code run faster. Just a random example of this is a bug from GCC from 2020. There's billions of these examples, but I picked one which is if you're doing memcomp and you're comparing something against a constant byte array, then this bug meant that GCC was trying to optimize that in the same way that it would optimize sterncomp. So it was sort of looking only for the first null byte in the array, which is often just wrong, and the optimization would produce bugs. The reason I picked this example is that it reminds me of a bug that I bumped into in some security software last century, a bug in GCC where I was using a flag to select between two byte arrays. And then GCC was saying, oh, I can speed up the selection if the two arrays happen to be the same. And it was comparing the arrays using, well, a string comparison instead of a memcomp. And so the arrays happened to have both initial null bytes. They were different after that. And so GCC produced wrong code. And this sort of thing happens all the time. There are many, many bugs in GCC and in Clang, and there's a fresh supply of new bugs all the time. Of course, it's not just the compilers that are wrong. It's also our cryptographic software that's wrong. So Pournat, for example, had some modular inversion software in 2020, which is modulo your favorite elliptic curve prime, is taking 6,000 cycles on an Intel Skylake CPU core. Now, to put that in perspective, if you look at OpenSSL, doing the same computation, it's doing a constant time Fermat inverter, which takes something, I think it was 15,000 cycles. And then if you're not doing inversion mod of prime, then there's a more general purpose BN mod inverse, which in OpenSSL takes 53,000 cycles and is variable time. So it certainly sounds better to have constant time, 6,000 cycles, compared to what's in OpenSSL right now. Except, look at Pornow's write-up of this. Then he says the first version of the code had a gap in the proof, and not a fixable gap because the code was simply wrong for some inputs. And then he says the revised algorithm and proof are believed correct. Is that the sort of code that you want to be running? Or suppose somebody says, here's code that is correct. Is that something you would trust? Or do you think to yourself, well, you know, cryptographers are maybe a little bit overconfident every now and then? Here's another example. I had a paper with Boyan Yang in 2019, which was introducing a different type of modular inversion, another algorithm based on what we call div steps. And this one, it's simple and it's fast, but the proof is not simple. The proof is very complicated, lots of cases to go through and too many to do by hand. And so we wrote some software which was saying, all right, the software goes through all the cases and then allegedly is doing a proof. But what if there's a bug in that software? And then the inverter could be totally wrong. Is this something reasonable to deploy? Lots of people say, look, this is not reasonable. We don't actually need the extra speed. And these optimizations are a source of bugs, so let's just not deploy the optimized software. Which sometimes gets us in trouble because, for instance, end of 2023, Kyber/, 2/3 of the Kyber implementations at that point had divisions with secret inputs, which depending on the context, compiler and so on, is maybe exploitable. And there were some demos of exploiting that with a timing attack. The AVX2 software was not using division. So it was one of the implementations that was not vulnerable, which does not mean that you should just think that AVX2 code is fast and bug-free because, for instance, Dilithium, the original reference software and the original AVX2 software both had exploitable bugs. They were interoperable, but not secure. I've been giving you various post-quantum examples, but it's not a problem. I mean, post-quantum software is certainly a disaster, but it's not just that. Pre-quantum software is also a disaster. I mean, looking at OpenSSL, starting in 2016, OpenSSL says it's a robust cryptographic toolkit. And since then, there have been hundreds of CVEs in OpenSSL, which a lot of them are up at the TLS layer, which I'm not talking about, but a lot of them are down at the cryptographic primitives layer, which is what I'm talking about. And this is kind of terrifying. I know what you're thinking at this point, because I'm thinking the same thing. Actually, I've been thinking it ever since I started this talk. Why, oh, why didn't I take the blue pill? This talk, it was supposed to be fast, constant time, correct. Pick 3, which sounds great. And instead, we're trapped in a post-apocalyptic cryptographic nightmare where our cryptographic libraries are slow, leak secret information through timing, and even when timing doesn't matter, have a never-ending series of devastating bugs. However, I still have some time left in my talk. This is actually a positive talk, and I want to tell you about what inspired me to give this talk, which is looking at the actual state of the art, which is something called S2N Bignum. And this is a cryptographic library, a new one, coming from John Harrison. He was at Intel for many years and then moved to Amazon. First release of this was in 2021. And if you look at the library, then what do you find in it? Well, there's various functions in the interface. For instance, for X25519, there's a function which is doing the Diffie-Hellman computation for you. And this has, well, a 32-byte results array. That's your shared secret coming out of Diffie-Hellman. There's a 32-byte scalar input. That's your secret key. And there's a 32-byte point input, and that's somebody else's public key. And then there's another function you can use to generate your secret key and public key in the first place efficiently. All right. So that's what the API looks like. Now, a lot of people look at this and say, wait a minute, this looks like a C API, and I have a different programming language. Well, you can use this via FFI. And FFI is easy in general when you have these simple byte array or just in general array interfaces. Those are the easiest case to get FFI working. Or maybe you say, oh, I want to have a key object and encapsulate these things more. And you can wrap that around this kind of interface. This type of interface is the most broadly usable interface. It's something you can reuse in all sorts of environments. This takes care of doing the computation, and then you can plug this into whatever applications you want. Now, the implementations of this interface, those are not as general. And let me emphasize this for a moment. The implementations are entirely in assembly. And that assembly is only for 64-bit Intel, 64-bit AMD, and 64-bit ARM, which is a lot of CPUs, but there's also a lot of 32-bit ARM CPUs, for example, and those, you cannot use this library on those. But let me just assume that you have one of these 64-bit CPUs that is supported, and then look at what the library is doing for you, starting with speed. Now, this is not just written in assembly, but it's written in assembly that's intended to be fast. And here's an example of that. If you look at the total cost, well, this is separated into Keygen plus Diffie-Hellman for X25519 using 3 different libraries on Intel Skylake, then, well, you see S2N Bignum has the lowest cost, and then OpenSSL in the middle, and libcrux as the highest cost. Does this difference matter? Well, that's something you can quantify. You can say, all right, let's translate the kilocycles here into, well, 1 kilocycle is about half a picodollar if you're buying your own hardware, paying for the electricity. Of course, it's a little more if you're using cloud services. And then you can say, all right, how many X25519 computations are we doing? It's about 90% of your TLS connections and various other applications, but how many TLS connections are you doing? You can quantify this. And then a lot of times you'll find, oh yeah, it's negligible cost, and we don't care about the exact cost or cost differences. But maybe sometimes you're in a situation where you're doing enough of these computations that you do actually care about the cost. And then, well, what people will sometimes say is things like this. libcrux is slower than OpenSSL. Now, it says nice things. libcrux sounds like it's a code quality improvement compared to OpenSSL, but it's slower. And I don't know if I can afford that because I haven't quantified how much that cost difference matters for me. And so I'm a little hesitant to move to libcrux, even if it's better software, because, well, it's slower, and maybe that's a problem, and I don't want to get in trouble. S2N Bignum, there's not a problem because it's faster. So even if you don't know what your costs are, even if you don't know that the speed up matters, and usually it doesn't, but even if you're thinking, oh, maybe I'm doing enough computations that it matters, well, S2N Bignum, it's faster than OpenSSL. So that's just a clear win. It's not a reason to worry about moving to better software. I picked Skylake because it's a common comparison platform, but you can look at lots of other CPUs and you get the same kind of picture. What about constant time? Well, we don't have the compiler messing things up, but you still have to worry because even if you're writing code in assembly, what if the instructions you're using are taking variable time? And this is actually, CPU manufacturers, it's been a problem for many years that even if you think, oh, this is a simple instruction that should run in constant time, maybe the CPU manufacturer introduces some timing variations, and so people can mess this up. 20 years ago, I had a paper on cache timing attacks on AES, and part of that paper I was looking at, can you use load instructions on Intel and AMD CPUs and do that in a constant time way? And my conclusion was in the following way: if you're careful inside the kernel and do the following, arrange your code as follows, then it actually seems to be constant time, but it's very fragile, and it relies on lots of undocumented CPU features. And of course, you should not write code that way. But even if you're doing simpler or more robust code, you have to worry, are these instructions taking constant time? And I started asking CPU manufacturers, can we please get some documentation guaranteeing that some instructions are running in constant time? And I kept asking and asking and asking. It felt like in the Shawshank Redemption, Andy Dufresne is every week writing a letter saying, can we please have money for the prison library? And just writing again and again every week. And in the meantime, for timing attacks, there are more and more papers which were saying, all right, here's a timing attack that succeeds because of complicated aspects of CPU timings on Intel and AMD chips, and sometimes ARM chips. And then smart card manufacturers would say, you should use a smart card because it's simpler and we'll keep your secrets actually safe. And meantime, people tried writing more and more software designed to be constant time. And it became more and more obvious to CPU designers that, yeah, there's actually value in making some guarantees here. So finally, in 2020, ARM sent some money for the Prison Library, data independent timing. Now, they didn't exactly lock down the details properly at the beginning. So, I mean, there's still something to be done there. But they were at the negotiating table and recognizing this is important and trying to make guarantees. And that's what matters. And then Intel 2022, data operand independent timing, same story of trying to make this work. Of course, there's more to be done. This is not the end of the story. We need AMD participating. We need the details nailed down. We need better tools to make sure that all of our software is really following these rules. But you can see this coming together. All right, what about correctness? Now, this is something where every API function in S2N Big Num has a theorem which says that the function works correctly. So, for instance, for the x25519 Diffie-Hellman function, there's a theorem called whatever subroutine correct, which says this machine code on ARM works correctly. And there's another theorem like that for the AMD Intel code. All right. This theorem is making assumptions about how ARM works. Part of the theorem statement is, well, if you have a CPU where an addition instruction does the following, a multiplication instruction does the following, etc., then the software that combines those instructions will have the following effect. If you look at other verification projects for software, then you see that they're often, instead of working with CPU instructions, they're working with the C language or some higher level language. And that might sound simpler until you start looking at the details and say, yuck, the C language specification is actually a very complicated thing. Plus, are C compilers actually interpreting that language correctly? I mean, compiling it correctly? And the answer is often no. So you get bugs because you're working on top of the C language and because your code is in the C language. Now, there is actually a correct compiler. It's called CompCert. And CompCert guarantees with a verified proof that it will correctly compile your C code into correct machine code. I have a link here to the CompCert license page, which says that you're completely free to use CompCert for absolutely anything non-commercial. Nevertheless, for whatever reasons, people are continuing to use GCC and Clang for all sorts of applications. And if you're using GCC or Clang, then any problems with those are going to maybe introduce bugs into your C software. So I feel much better having a specification of the CPU instructions as the basic assumptions for S2N Big Num, having these theorems saying that it works correctly. Now, to be clear, the CPU specification is still maybe not correct. There could be mistakes in those specifications. I mean, whoever wrote those, maybe they're not correctly describing how a CPU works. Of course, there are all sorts of tests, but this is something that can be improved. I think there's a non-zero risk here, and there's more we can do to really eliminate this risk in projects that are working with CPU specifications. I don't want to minimize the risk here in the sense of I don't want to make it sound like there's no risk. There is a small risk. More can be done to improve this. Another thing that can go wrong is the CPUs might not work the way they're supposed to work because of mistakes inside the CPUs. Things like Zenbleed, I mean, just bugs in how the CPUs are designed, or the CPU, Intel Raptor Lake chips are just drawing too much power, and then that makes them make mistakes. And you really have to engineer the CPUs properly. So there's something that has to be done on the CPU side to make sure that our CPUs are working correctly. Maybe the theorem statements are not what we want. So, I mean, I said there's a theorem which says subroutine correct. Well, if it's named subroutine correct, does that mean the subroutine is correct? No, you have to look at the details. The fact that there's a theorem, that is not telling you that the theorem is saying what you want. You have to look at the details and see, yes, the theorem is saying that this is the crypto system that we want. That's what the code is computing. Now, all of the things that I'm talking about, these sort of controllable risks, these might feel like they're ignoring the big problem with theorems, which is that people make mistakes in the proofs, like the mistake I mentioned before. But this happens all the time, is that people think they've proven something, and they haven't actually proven it. But this is where S2N Big Num is really spectacular. S2N Big Num has all of these proofs being checked by one of these computer checking, proof checking systems. And in particular, by the one that has the maximum assurance, which is one called whole light. This has a very small kernel compared to all the other proof checking systems. And that kernel has been very carefully reviewed and proven to work correctly. And I mean, there's tons of assurance for this kernel. So we really feel comfortable, anybody working with whole light, which I've also done somewhat, it feels really comfortable that, yeah, things that whole light says are correct proofs, those really are correct proofs. It doesn't mean that the theorems that come out are what you want the theorems to be, but if it says this is proven, then yes, it's checking it from the basic rules of logic and doing that correctly. Let me emphasize what this means for an auditor. So an auditor who's saying, oh, I have traditional cryptographic software is saying, I have to worry that every single line in there could be a problem. I mean, it's all part of the trusted computing base. You have to go through every line of your software, make sure it works correctly, think through what's being computed. Is that what you want? And if you haven't done that, there could be a bug anywhere. So it's tons of work because of tons of cryptographic software. If you instead have a computer-checked proof of the software, then you're automating that process. You're automating having the computer is going through every line of the software. The computer is going through every line of the proof and making sure that your theorems are actually proven. And that reduces the auditing task. It reduces the trusted computing base. At this point, your trusted computing base is just the theorem statement of here is the small statement of what this function is supposedly computing. And well, that's what the proof says, yes, it is computing that. And you have to check, is that what you want? Plus, you have to check the proof checking tool like whole light, and that's something which is shared by tons of proofs, so it's been done already. All right, so you've automated the painful part. You've reduced the trusted computing base down to just a small theorem statement for each of these subroutines. As an example of how this improves speed, when you have these when you have this auditing picture of you only have to check the theorem statements, and you just don't have to look at the code and the proof. And if that's something, if it's more complicated code, a tricky proof, then the computers checked that. And so, for example, first version of S2N Big Num was happily using some fast inversion software, which was 6,000 cycles on Skylake, so the speed that I mentioned before from Thomas. Except the difference is it had this computer check proof. So you feel comfortable using this fast software because as an auditor, again, you don't care whether it's simple software or complicated software as long as the computer is checking every single line of that with a trusted checking program. Now S2N Big Num is using even faster inversion software, 4,000 cycles on Skylake. And that's something which, again, has a computer check proof, like everything else in S2N Big Num. The auditor is just looking at the theorem, which is the same theorem. It just says this code is doing inversion correctly. The actual details of the code have changed, but the conclusion is it is doing modular inversion. If you're checking a higher level function like elliptic curve Diffie-Hellman, then you don't even have to look at the inversion theorem. You just have to look at the theorem saying that the X25519 computation is done correctly. I think, let me just check on time. I think I have a little bit of time where we can actually look at the statement of the theorem. Now, it's 18 lines long. The high-level overview of it is the following 5 lines. There's some punctuation. Any new programming language got to learn the punctuation, unless it's COBOL. COBOL, no punctuation to worry about. Anyway, in this language, there's something which means for all choices of some variables that are listed, if assumption 1 is true and assumption 2 is true and assumption 3 is true, then a certain conclusion is true. Okay, that's what theorems sound like. If certain assumptions are true, then a conclusion is true. The first assumption says aligned 16 stack pointer. And stack pointer is one of the variables. And I look at this and I think, oh, that probably means the stack pointer variable is a multiple of 16. Okay. Of course, if you're doing a complete audit, you have to check the definitions that are being used. And if you look at the definition of aligned 16 means 16 divides the value you're looking at, but it also has some 16 divides 2 to some power of the length of the word that you're looking at. And you have to think for a moment, wait a minute, that doesn't sound like it's part of aligned, and why is that a reasonable thing to put in? And eventually you can convince yourself that this is a reasonable thing to say about alignment, but it's it's not something which you might have expected just seeing the word aligned. And there could be traps anywhere in the definition, so you do have to check carefully. But these definitions are reused across all of the theorems about all the different functions that you might be computing. All right, assumption 3 is, if you look at the definition of non-overlapping, it's talking about regions of memory that are not overlapping, not aliased. And this particular assumption is that the 32-byte result array is not overlapping your code. Your code is, there's a PC, your program counter, it's another variable which is going to be assumed to point to your code, and then the length of that is 0x27F8, so about 10 kilobytes. And again, you have to check what non-overlapping means. And then, okay, yeah, it makes sense that there has to be an assumption like this. I mean, if the result array were in the middle of your code, then all sorts of bad things could happen. So to conclude that we're computing x25519, you need some assumption about your memory regions being separate. Assumption 2 is another of these non-overlapping. There's a little more punctuation here. This all means that everything inside brackets is not overlapping with some range on the stack. This says that the code and the input and output arrays are not overlapping 384 bytes on the stack, which is the amount of stack space used by this code. Which, okay, again, seems like reasonable assumptions about how you're supposed to call this function. Of course, you don't want your inputs and outputs to be crashing into the stack space you're using for the function. All right, what about the conclusion? Well, this is where it starts involving the actual CPU. The conclusion says ensures ARM, and then there's some preconditions and some post-conditions, and may change. I'll skip that. What the ensures says is that if you have your CPU satisfying the preconditions, like if the current state of your computer is doing what the preconditions say, then the computer will, after following some instructions, satisfy the post-conditions. And we'll look at these pre and post-conditions for a moment. The ARM, that's where the definition, the specification of the ARM instruction set is. And that is thousands of lines long because there's a lot of ARM instructions and each one takes some lines to specify. And that's something that is, again, important to audit to make sure that that's correct, but it's shared by all of the code in S2N Big Num, which is written for ARM. So it's one time instead of something that is repeatedly looking at each function. All right, the preconditions, one of them says that your code is loaded into the state at the program counter. PC is this variable, which before was non-overlapping with things. And now this assumption says that curve 25519, x25519, byte MC, whatever that is loaded into the CPU state at this address. Now, when you're doing an audit, you do not have to look at the definition of that 25519 MC. It is the machine code which the theorem is talking about and which the proof is looking at in detail. But you don't have to look at the code. You don't have to look at the proof. You just have to look at the theorem statement. There's a little tool attached to the proof which automatically checks that the machine code definition used in the theorem is actually the same bytes as the object code on disk that you got by compiling S2N Big Num. So good, that's what you need to know, is that whatever that code is, which as an auditor you do not have to look at, that is matching what the theorem is saying works correctly. There's another preconditions on, well, that the capital PC register has the lowercase PC variable for saying the program counter, that's what's pointing to the code, that the capital SP register is the stack pointer variable, and something about the return address using X30, which on ARM is where you put the return address for a function. And then there's a few more preconditions about the arguments. So there's this result and scalar and point, those were the arguments to this function. There's an assumption that the scalar is pointing to 32 bytes, which have a big integer n, a 256-bit integer n, and the point is pointing to a 256-bit integer x. And again, you have to look at, when you're auditing these things, you have to check what C arguments means in principle and read memory and so on. And then the post condition, this is where it's finally getting to x25519. The post condition says that after running some instructions, you will be returning to whatever return address was in register X30, and then the result array will have a big integer, which is exactly RFC x25519 of inputs n and x. And then you have to look as an auditor at the RFC x25519 definition and check, yeah, that matches the RFC. It is x25519. All right, so that's what an audit looks like for this S2N big num theorem, which for me, so here's how I feel having gone through this and also looked at various details, is I've written X2519 software and I've verified quite a bit of that software, not just my own, and it takes time to do that, which is much more time than what we just looked at. This was much less time, even looking in more detail at the definitions and really saying, yeah, this is right. It is much less time to do this audit than to audit the actual code, because again, that's automated. I do think that a lot of what we were looking at can be improved because, for instance, things about the stack and the registers and X30 being where you put the return address on ARM. I mean, this should all be just encapsulated inside, let's say, a C call instead of that C arguments. It should just be, you just want to say, we call this function with inputs which are pointing to some 32-byte arrays, and then the output is going to be pointing to a 32-byte array, which is the output of this RFC X25519 function. And whatever specification of that C call should include all the normal details of things like stacks and so on that you shouldn't have to worry about. But despite having boilerplate in the theorem statement, it wasn't that painful to go through, and it's much, much less work than auditing a piece of code normally. And if you have another piece of code which is like improving it, speeding it up, doing another platform, the theorem statement looks the same, and you can just reuse that. You read it again, and you're like, yeah, I've checked that already, and you don't have to worry about the new code, the new proof. Somebody else has written that, and as an auditor, you don't have to worry about that. All right. What does S2N big num mean for other libraries and for the cryptographic ecosystem generally? Well, let's look at this from the perspective of, say, OpenSSL. I mean, obviously, S2N big num, to the extent it's providing functions that OpenSSL also provides, S2N big num is competing with OpenSSL. So what is OpenSSL going to do to fight against this competition? Obviously, speed arguments don't work. Could try saying OpenSSL is robust again, but somehow after the 100th CVE, that doesn't work very well as an argument. Could try saying our programming language is better than your programming language. Oh, wait a minute. OpenSSL also uses assembly? All right, never mind. You could try OpenSSL Stockholm Syndrome, or you could maybe say it's better to just use S2N big num inside OpenSSL. I mean, OpenSSL has its code which is doing X25519 computations and various other things that S2N big num can do. Why not just say, if we're compiling for these 64-bit platforms that S2N big num supports, then if we're calling these functions, just call S2N big num. Replace the previous code with this better code. And same question for lots of other libraries. I mean, this is the biggest problem we have auditing the cryptographic ecosystem is there's so much cryptographic code out there, which in part is because, well, there's different cryptographic functions, but a lot of it is because there's many, many implementations of these functions in many different libraries. And sometimes for speed reasons, but a lot of it is things like people are using the Go programming language and think, oh, we should have a Go library for cryptography because, well, that's going to be higher quality code. Go code is always higher quality than C code, and so we should be doing a Go library and using that. But it's another source of bugs, having another library in whatever language. We can really share better code across languages and reduce this auditing problem. Instead of having tons of different libraries with tons of different bugs, let's take one very carefully checked piece of code and reuse that across a lot of different libraries. This seems like an easy win for OpenSSL, seems like an easy win for basically every other cryptographic library you can think of to use S2N big num whenever possible. I think in the interest of time, I will skip 2 slides on what it looks like to extend S2N big num. And I'll just have my last slide here on the bigger picture. I think that the message that you should get from this talk beyond, well, take a look at S2N big num, the message here is really that verification, which used to be this sort of theoretical thing that maybe could be done, it's actually part of the cryptographic ecosystem now. And if you're not using verified code already, you should start looking and saying, hey, can we use verified code? And it's just popping up all over the place. For instance, later in the conference, there's a talk, PQ Connect, which is about all sorts of networking issues and integrating post-quantum crypto. But, well, one little piece of PQ Connect is formal verification of the handshake protocol in PQ Connect. And it's just a tool that you can use, and it's up at the protocol layer, separate from what I've talked about. For a broader view of what's going on with verification, there's a talk which is all about high assurance post-quantum crypto. And that one also will tell you that libcrux is not so bad, in case I was scaring you away from it. libcrux is trying to deal with AND1 and other issues like that. More broadly, it's going to tell you, like, here's the big picture of what's going on. I've also got a bunch of links to other projects, which are interesting projects for doing high assurance cryptography. That's it. Thank you for your attention.
Hi, Dan. Karthik here, Karthik Bhagan. And of course, I'm a complete believer in the formal verification story. The last talk there is going to be by me. But I was wondering whether you saw, the story about the compilers is, of course, extremely scary, about how pretty much they always seem to destroy what you want to do. And S2N and a lot of these things are directly written in assembly. Do you see any situation in which crypto, especially new crypto, right? X251 is 10 years old, it's a nice RFC. People have seen this many times. And it's fairly stable, right? There's no reason to change it once you've written it. So you do one big proof in assembly, it's great. But do you see any situation in which you might want to write and verify crypto in a higher level language, like C, like Rust or something? Or do you think for crypto, let's just stay with assembly for everything?
I was understanding the core of that to be, should we just use assembly and stick to assembly versus should we have some verified crypto code in C and Rust? So to me, I see the higher level languages for verified code as being sort of a temporary status if we haven't had time to produce verified assembly yet. The closer that we can get to having code that's what the user is actually running in the end is machine code. Of course, you can point to different environments, like what if you have Java code inside a Java VM and so on. But the normal situation is you're calling cryptography, which is in machine code. And the closer we can get to verifying that, the better assurance we have. And it's also something which is good for speed, and it's something, to the extent that there's deployment issues related to speed, we get around that by focusing on a low-level language. And it's something which can plug in so many different environments. Rust, it's something you can plug in various places, but it also, unless you're doing the no standard library versions, which lots of Rust code is using the standard library, it's hard to plug the Rust standard library into a lot of environments. And that sort of thing, if you have assembly code with a nice simple interface, you can use it in C, you can use it in Rust, you can use it in Go, even though Go has a somewhat different ABI. You can use it in Java if you're careful about how you do the integration, et cetera. And so I think for having something that we can use anywhere, the arguments for higher level languages, I understand the simplicity of getting something verified in those languages, but when you say we want the highest assurance, the best usability, along with the best speed, just in case that matters, then it's really hard to compete with assembly. So I do see assembly as the future here, and S2N Big Num is making the right choices there.